Hey, I'm John Furrier with theCUBE here in the CUBE studios in Palo Alto in heart of Silicon Valley for a special CUBE conversation where we're breaking down the future of AI factories, AI infrastructure, and an exclusive look at a stealth startup coming out, Resolight.ai. Ofer Shapiro, the CEO and co-founder, is here in the studio. We're here this week for GTC and all the madness involved and all the opportunities in AI infrastructure. Ofer, great to see you. Thanks for coming back in.
Well, thanks for having me, John. It's great to be here.
Appreciate the briefing yesterday. You guys are pioneering photonic processing, which is probably the hottest area right now in these AI build out, all these data centers, these AI factories, large scale clusters, and now the edge is emerging. Networking and CPO, co-packaged optics, is the hottest area. That's where the action is, that's where the throughput is, that's where the gains have been, that's where all the hype is, and that's where people are excited about. You guys are coming out with something specific out of stealth. Talk about what you guys are doing, the problem that you're solving, and what is your solution?
Happy to do that, John. So the first thing we have to recognize that AI is not just about GPU, as you mentioned, it's about the network. You need to connect a large number of GPUs together. And at some point, you have to get outside of a single rack. And the only way to do it is to go optics, and this is what drives all this excitement and interest in CPO, LPO. We've heard a lot of announcement about it in the last few weeks. So this is great, but one thing that we need to understand is that once you have all this massive amount of information carried over light waves, it's kind of a shame to downgrade it back to electronics just to process it and route it in a switch. So it's essentially like you have a highway and you put a stoplight just in the middle where everything starts to flow. So what we recognized, you have to introduce what we call photonic processing, which is to process the traffic of light in the light domain without down converting it to electronics. And this was considered something that's not possible before. It's kind of the holy grail. But in fact, it is possible now, and that's what we're all about, addressing this networking bottleneck, which touches every aspect of this industry.
Jensen Huang, the CEO of NVIDIA, talked to us in a private analyst meeting. We weren't allowed to record anything, but I did write it down. He did give a little Easter egg comment I want to get your reaction to. He said we have to take the electric out of it, and he's kind of pointing at the inefficiencies between the processor units. They have Grok, they have other things, they have memory. There's a lot going on around these high performance chips, these now systems. And I want to get into it because you guys solve that problem, and I want to get to that. But first, explain the product. It's a chip, and where does it sit? What does it do? Because you see CPO as a key ingredient in all of these large scale systems. It is the key feature that was being talked about in NVIDIA's GTC, is the key feature being talked about in all the semiconductor components that bring the systems together in the interconnect. Talk about the product and then specifically this electrical problem.
Absolutely. So first, it's not a chip. It is powered by a photonic chip, but it is a box. So from the outside, it would look like a network box, rack mountable, an optical switch. But the inside is where all the magic happens. So the inside is photonic processing, which means that compared to a traditional electronic switch with an optical interface, where you have an optical input that's converted to electronics, and then the ASIC that is in the heart of that legacy chip is reading and writing every bit individually. And the whole race, the incremental race in this industry, is how to take those X number of picobits per joule and squeeze it to get a little bit better, a little bit better, a little bit better. Those are all incremental improvements. Whereas what we do is we basically deal with all of those in bulks. Because it's such a large amount of information, you have to change the way you handle it. So with photonic processing, you basically say, here, I'll deal with a megabit at once. Here, I'll switch a megabit here and a megabit there. And because the information is so high speed, it's still extremely low latency, but at the same time provides economy of scale, if you will, in dealing with the bits. So it reduces the amount of power required by the networking gear by an order of magnitude, increase the throughput by an order of magnitude, reduce the number of network connection, which is a huge problem, by an order of magnitude, and even takes the number of transceivers down to 1/4 of the original number of transceivers. And we all know how this is a huge issue in the supply chain. Just that's a problem on its own. So it touches it touches every aspect of the problem.
So bigger, fatter pipe connection, so you can move more data faster.
That's correct.
With photonic processing. It seems to be over the past, I'd say 8 years, it's been very incremental. We've covered the NICs, which was, no one was covering that stuff, but now it's super important. The NICs are connected to the GPU. They connect to another NIC, go to electrical signaling, go to another NIC, and then to another GPU. So there's a lot of like hops, I won't say hops, but like connections. That's the state of the art today.
It's actually even worse because there's a limit of how many GPUs can connect to a single switch. So people are building two-tier architecture where the switches connected to switches. So you have even more hops and even more conversion, and simply doesn't make any sense. And because it's so limited, that's why today people are making the differentiation between scale out and scale up. So scale up is what's happening inside the rack when you actually give the GPU all the bandwidth that he wants. So that this is a problem that sort of the industry knows how to handle, but when you got out of the rack, you lose a lot of the bandwidth, and that's exactly what this technology comes to address, and that's why we call it scale everywhere, because it gives you the breadth of scale out in scale up bandwidth.
So if I understand this correctly, the racks take up a lot of real estate for the switches. We see that in the displays.
Right.
You got the GPUs, and there's a whole section, in some cases, dedicated machines, boxes, just for switching. Mm-hmm. So switching seems to be the element that's turbocharging the growth of the GPUs. You're saying you guys collapse those switches down, or what's the impact? What's the problem is, okay, I see the problem that you solve. You get more bandwidth, lower latency with photonic processing, take out those electrical signaling and conversions, bits, now you got megabytes. What's the solution? What happens?
So if you look at those switches today, you see that they're processing 100 terabits per switch, which sounds like a lot, but it's not that much compared to the requirement of the GPU. So where you would need otherwise 10 boxes to deal with 1,000 terabits per second, in our proposed architecture, you need one box that can deal with this bandwidth. So you free up a lot of space in all these racks for the GPUs or for other things that you need to do, while reducing the power, while providing great performance, and even allowing you to dynamically cluster GPUs from different racks, which is another level of complexity, or addresses another level of complexity that this industry is grappling with, which is what happens when you change a data center from dealing with inference to scale up, or vice versa, or come up with a different model requirements. You really need that flexibility. You cannot have the networking infrastructure determines what happens with the GPU. This is absolutely crazy. And that is something that the scale everywhere architecture addresses in a great way.
Yeah, I've been covering the networking aspect when KV Cache came out, and now Dynamo, you're seeing massive advances. And you're seeing storage and memory really coming closer to the GPUs and the XPUs. That's expected. Now the interconnects have to work. This is where CPO is popular. Recently, Celestial AI was bought for, I think, $5 billion. Yep. That's a CPO product. And we know NVIDIA has some, Broadcom has CPO, others. Is that good enough? And how do you compare? Because let's talk speeds and feeds, because like now I'm talking about numbers. They need more performance, and that's clearly the message we're hearing at the events in the industry. The interconnects are the key. Compare the kind of performance and then the changes in the racks that happen because of it.
Fantastic. So first, we love CPO. We love CPO, we love LPO, all the things that ends with O for optics. This is the infrastructure for our solution to flourish in. The one thing to understand is that CPO on its own is not magic that solves everything. It is an interface which is far superior than traditional copper. It allows you to send more information on a single connection for a longer distance, and that's fantastic. But you still have the question outstanding on how you process all this information. Like if you free up one constraint, you have even more information in the network. How do you process it? So without photonic processing replacing the old architecture of switching in the network, the CPO helps, but only incrementally. Once you have CPO plus photonic processing, you have this breakthrough that addresses all those challenges that your audience keep hearing about.
What are some numbers? Share the scale. Where are people today and what are you bringing in?
So our vision, and we're not ready to announce specific product details, this would come later this year. We're just coming out of stealth mode, but directionally, we believe that these type of systems would take scale-up bandwidth from hundreds of GPUs to hundreds of thousands of GPUs. That's the vision. And this is driven by this kind of new architecture and a success of CPO and LPO that other vendors are bringing to the table, which is an absolute requirement. It's sort of a perfect storm of exponential demand and the focus that people are now putting on operational excellence, and also the fact that open standards are emerging now to support this growth. This is key.
One of the discussions areas, you mentioned scale up, that's a big one because of the racks. NICs and CPOs involved heavily in those. Scale out is another one. So you're scaling up and scaling out, and then you're scaling across. You guys have a term called scale anywhere. So explain the scale up impact with your product, and then scale out, and then scale everywhere.
So I think the first thing is to understand what is the difference between scale up and scale out. Scale up is where you give the GPU essentially in a low latency fashion all the bandwidth that it would want to connect to other GPUs. And scale out is when you go when you go outside of the rack and you have to, because of technology limitation in the switches, you have to kind of dial down the bandwidth. Kind of you're losing about a factor of 1 to 10 these days. And you don't maintain the same latency budget. So scale out allows you to connect more, but not in the same efficiency and the same performance. What we're proposing to do is to eliminate that barrier. In our world, optics from the GPU, CPO, all the way with photonic processing, the scale up can reach the same level in terms of number of units as scale out, but without losing the performance. It's kind of the perfect solution, the holy grail that people initially thought it's not possible, but it is possible to do.
A lot of conversations happen, and I hear the word copper, because copper is still hanging around.
Right.
And there's benefits to that, and we hear them, but no one's unpacking why copper and why CPO is taking over. All the analysts raise their hand. They say, you know, where's CPO fit with copper? Obviously, then it gets explained. There's a necessity. It's because of the distance and things are closer together. How do you impact that limitation?
So copper is great when you want to communicate to a distance of 1 or 1.5 meters. And that's why when today kind of the standard response to let's put more resources into the scale up, let's build bigger racks, 42-inch racks instead of the 19-inch rack that we all grew up believing it's a universal constant. It is true that within the rack, it might be more power efficient to use copper. But when you take into consideration the fact that eventually you have to get out of the rack and you'll have to go optics, you may as well go optic immediately. And once you go optic immediately, then even the switches within the rack eventually will transform to being optical. There may be a step in the middle where some of the switches inside the rack are still electrical with copper and some optical outbound, but eventually it would all fall to a single full optic end-to-end architecture.
So I guess the core is you solve the problem of bandwidth. That's the number one thing. What other benefits come with the optic processing, photonic processing?
So we solved the bandwidth, as you mentioned. So, but with solving the bandwidth limitation, we also reduce the number of network boxes and the number of network connections. So let's visit them one by one. If you need 10 times less network connection, that means 10 times less optical fibers you have to worry about with all the concerns about how all these connectors, how do you do the cabling, how all these connectors perform over time, and so on and so forth. So 10x reduction of a large problem is important. Power in the switching, it reduces the requirement by a factor, by an order of magnitude, which is also, of course, great because we know that all these data centers are limited by power. So the more you address this, the better you can scale. And last but not least is the issue of performance, that you can integrate GPUs on multiple racks. And then you may not have to do those very thick racks, which are kind of an engineering marvel on its own, but stick with simpler 19-inch rack mountable, 19-inch racks that actually may fit more existing data centers. So that's also a good thing because it would allow telecoms to get back into the game and use some of their own older facilities for this.
So you actually impact the packaging of the racks for sure.
Right.
On the NIC side and taking away some of the things that were engineered for that incremental gain with this limitation of moving the bits around. Now you're doing megabytes. This is extreme engineering. So I have to ask you, why isn't anyone else doing this? What's the...
That's actually a great question, and
it's obvious.
Yeah, and part of the game of being in stealth mode is like you say, okay, what happens if someone else is coming with the same solution? So I think if you think about holistically, how do breakthrough come into the world? So there's two concepts. One, you can take existing products and incrementally improve them, or you can have a leapfrog. The leapfrog kind of breaks an old architecture, and it needs usually startups to do it because the existing players, they're kind of bogged down by the management of what's going to bring me revenue in the next quarter and the next quarter. That's why startups exist. Another aspect of it is you have to rethink the way the information is packaged in order to enable this. So if you're working within, if you're an expert in how it's done, it's harder for you to figure it out. You have to come up and say, oh, I want to bring in an idea from a different environment that works, which, by the way, I had the privilege to see two other transformation of architecture that follow the same template of a new way to send information over the wire, and which enables a better server architecture that circumvent the bottlenecks, which is a great thing.
Well, certainly we heard directly from Jensen Huang on stage at the keynote. He said, AI can't wait. Humans can wait a second. AI can't wait. So all the emphasis on feeding, I call feeding the beast. Feed the data into the AI systems, GPUs and these clusters, and interconnects big part of it. You mentioned number of connections, latency, networking requirements, energy. These are things that are now check boxes. Talk about your solution. How do you address some of those things? What's the impact on number of connections, and what does that mean? Latency, you mentioned a little bit on the scale across. That's key, maintaining that purity of bandwidth, latency between two racks, and then across other geographies, optics works too.
Yeah, I love the analogy of feeding the beast. So what we're seeing here is a crash of an exponential demand with traditional incremental improvements on the networking. That's the fundamental issue. So when you look at our solution, let's just touch the number of connections, which sounds like the most trivial thing ever. So when you want to connect thousands or tens of thousands of GPU, and you look at all the cross connections that are needed, you're looking at frightening amount of network connections. And at the end of the day, you could sketch it out on a whiteboard or have it on a procurement spreadsheet. But at the end of the day, some engineer have to go and plug in and plug out hundreds of thousands of optical fibers. And one of them has a flick of dust on it, and who knows what this now does. So for me, this is like, already an extreme engineering. And I look at that and I say, you got to take all these big problems down by an order of magnitude. So 10 times less boxes, 10 times less connections. That addresses a huge issue. Bandwidth is also key, because if you cannot provide the same bandwidth that the GPU really, really wants when it wants to scale up, then the scale up is limited to a single rack. Then you get bigger racks, which are incrementally more complex, and at the same time limited, because there's a limit of how much you can do.
Yeah, I see in the presentations they go through great lengths, whether it's Jensen or someone else on stage at another conference, to explain the math involved. X number of GPUs, and it's always kind of a formula that's always based upon switching. Because when you peel back the onion, you say, okay, how many GPUs can I put on a rack? That's the end of the day, that's what I want to know.
Right.
That's the money. The switches are the key variable. That's the dependent variable on what allows the GPUs. So do the math for us again on what you guys impact on that number.
Right. So if you just, it's hard sometimes to follow large numbers, but let's start from a very simple example. In an NV rack, NVL, you see 72 GPUs that are connected through 18 switches. And you think about it, right? So the network boxes are to the ratio, has a ratio to the endpoints of 4:1. Now, if you think about feeding the beast with millions and millions of GPUs, probably tens of millions when you look at the accumulated install base in a few years, or maybe we even surpassed that number already, divided by 4, if you want to get the scale-up performance, then you get many millions, or perhaps also tens of millions of switches. Times it by 100, you get the number of network connections. This doesn't add up, okay? You have to take, to address this problem.
It's going to hit a wall.
If it's not already. So people are complaining about it already. What happened so far, we were really busy about proving the utility and the functionality of these models. Smarter and smarter models, which provides things that we wouldn't even imagine a few years ago. But now, when it matures, people start to think about the business case, the operational aspects of it. How much does it cost? And they start to see that it adds up. And not everything has a business case. And we just sat on another panel that Jensen chaired in an NVIDIA event the other day. And we heard him talking to a bunch of CEOs about all these new models that would require probably 10 times more, 100 times more compute resources, and they basically said, more compute, more intelligence, more revenue. So Jensen actually stopped the conversation and said to the crowd, you heard that? More compute, more revenue.
Yeah.
But how do you provide 100 times more compute where we could barely keep up with existing data center requirement? You have to do something better to scale it up. And the networking, it's not the only solution, but I think
it's a core solution.
It is going to
it's
be
a bottleneck today.
Focus area.
It will be a bottleneck as the data rates come in. You got to feed the beast,
Right.
And he even talked about you want the latency. Network connections causes more complexity. The software has to get smarter. Talk about the scale anywhere, because I think this is interesting. Because he also said something on stage, Jensen did, around he can imagine super AI factories, just data centers, just racks everywhere. We've heard complaints here on theCUBE from some of the neo clouds where they spend a lot of money, they get all this gear, they build the AI factories, and they train. And now it's inference. Now they have to kind of retrofit the architecture for inference, buy more stuff, but they want to leverage the existing stuff. So scale that out for a minute, in pun intended, to what Scale Anywhere does, because if you're adding stuff, the use cases might require a different kind of AI intelligence. Training, inference, reasoning, what else, OpenClaw is going to be out there. Edge is right around the corner, so you get the super factories, the edge factories, metro factories are coming. You're going to need to have connections. Photonics fits, I think, beautifully here. At least my instincts tell me that, can't do copper across a couple miles.
Of course not.
And so, okay, so I got all this, I got this one distributed computer acting as one. That's distributed computing. Okay, so now, where does the photonics processing share anywhere concept and lay that out?
Right, so the key thing is the ability to software define the infrastructure. So think about today, we started to develop I don't know how many terms you just covered in, you used the word scale, okay, in so many ways. We actually have been in another great event for the Optica Executive Forum event, where they actually had separate panels with separate vendors for the scale up, scale out, scale across, all these, and people were also talking about scale in. When you ship GPUs today and you install them in a rack, you kind of determine the way it's going to be used by the network connection that you provide to them. And of course, touching that afterwards is a huge overhaul. So it's not going to happen in one day, but the conversion to a network interface that is the same, no matter if you want to use this particular GPU now for inference, for training, for maybe another purpose in the future that we didn't think about today, or a new modality. And it doesn't matter if it works on its own or with 500 other GPUs across the data center that happens to be available right now. That's what scale everywhere means. And it's hard for people to envision that because we all got trained to, there's a switch for this and a switch for that and a switch for the other thing. And each one has its own variant, and you have to commit to it. And it's just not, it just shows that technology limitation is dictating the way we want to use our capital equipment. And that's not a good thing. You want to move to software-defined. That was the breakthrough in telecom. That will be the breakthrough in networking as well.
It's interesting. When I look at some of the things you're doing and some of the things that we're covering in the industry, it's like an engine in a car. This little upgrade or feature, photonics processing, seems small, but it's big because it actually makes the engine run better. That's the networking. And networking has been the key to success in the AI infrastructure, because that's what's moving the data around. And again, everything's getting closer, but now you have a lot more density both in the racks, in the data center, and then now with AI factories everywhere, you're going to have density of factories. So the interconnect is essentially networking. Small, short, long.
To continue analogy, if the GPU is the engine, the networking is the transmission. And in order to actually be able to switch efficiently and make it run on different terrains, you need efficient transmission. If the transmission is not good, you can have the best engine in the world. The car will not drive smoothly.
So you're a turbo mode, turbocharging the factories.
Absolutely, yes.
Now that you're out of stealth, you got just recently, past week, I know you're not revealing all the details. Reveal a little bit about what you can talk about publicly and some of the reaction, because I'm sure there's going to be a lot of naysayers out there.
Oh yeah.
Definitely when they watch this video and they look at some of the materials, I'm sure Broadcom, all the NVIDIA, they're going to assemble their A-team and be like, okay, what do we got? What's been the reaction? What can you share?
So you have to differentiate between kind of public and private reactions, okay? Publicly, everyone has their own talking points. Privately, we've seen a very compelling response, including, you meet with people, and on slide 2 we say, how could we, do a proof of concept together? The problem is not a secret. People may not address it publicly too much because they don't want to kind of...
They don't have an answer.
When you don't have an answer, you better not talk about the problem. When you do have an answer, it actually makes it more interesting, at least for the people that are the first movers. This is not the first time I've introduced disruptive technologies to the market. And publicly, I'm fully expecting people to say, oh, this is a science experiment.
It's never going to work.
It's never going to work. You have to change things. But the fact is that at some point, you're outgrowing any technology, and you have to stop doing sustaining engineering and move to the disruptive solution. And disruptive, as the name suggests, it disrupts some people. And initially, they object. Actually, initially they laugh, and then after that they object,
Yeah.
then they fight, and then they lose, and this is
It's
an
interesting.
age-old metaphor.
NVIDIA is a great example. Two final questions for you. One is the extreme engineering, which I pointed out, which I think this is an example of. They use the word extreme co-design. So obviously look how fast they got things to the market with, say, Grok, for instance, that acquisition that happened very fast. They can move pretty fast on co-design. Co-design seems to be the thing. How do you see that fitting into your plans? And also I learned at NVIDIA, things like Omniverse came about because they thought about how to write software differently with computer vision. So, you know, they had to rethink architecture on how they were solving the problem. So what made you think differently from an architecture standpoint? And then what's your thoughts on co-design? Because now this comes to market, I'm imagining that smart money will come in, smart players like the engineering teams will say, okay, we got to get this in because it does solve a problem.
Right.
Architecture thoughts on how you came to this, and two, your thoughts on extreme co-design.
Yeah. So the way we came to this is we like to find a really big problem, and it has to usually come with the people that are trying to address it with the old ways. They're building extreme engineering projects, which this definitely complies. And then you just have to say, if I only could have changed this parameter. And here, as I mentioned, you have to change the way information is sent so the server can become better. In terms of the strategic plans on how to do it, when you come out with something like that, you still have to realize that even though we think, you know, we have the best architecture to do it, it requires a change, and you have to do it with cooperation with other players. In the context of standards, but also in the context of co-development and integration and bringing solutions that are combining the best of all worlds. And we already started this process. And as I was hinting, I hope to be able to make some interesting announcement later this year. And I promise to come in and tell you about it. So.
All right, Ofer, great to have you on. Resolight.ai is the company coming out of stealth here on theCUBE. Ofer Shapiro, CEO and co-founder. Again, solving the networking problem really is not a problem, it's more an acceleration of what networking is doing, which is the key ingredient to make these super AI factories and all AI factory systems work. And we're going to continue to see it's the hottest area in the area of AI infrastructure because it's going to power the systems. I'm John Furrier here at theCUBE. Thanks for watching.